So it is indeed the 11th. So we are given this limit and we're asked first to simplify the function. So forget about the limit for a moment. Where do we start? Where is the starting point?
Plugging in the,
Forget about the limit. We are asked to simplify the function. Where is my starting point?
Absolutely.
Of course, the absolute value 1 minus x has two options, 1 minus x if 1 minus x is greater to 0, or the opposite of this, and you can write it like this, when 1 minus x is less than 0. So this is my starting point, no matter what I do. Any questions on this? This is the formal, yes, please. Paige, go ahead.
They're kind of dumb, but I put negative x plus 1.
That's fine, same thing.
Okay.
It's still x minus 1.
Okay.
Yes, I saw that, perfect. So then when you solve this inequality, you get x less than or equal to 1 because you have to move x to the other side and you have to read it from this side. X is less than or equal to 1. You don't have to solve the second one. Don't even look. If this is less than or equal to 1, this must be greater than 1. Don't waste your time. Don't cross it out like that. I'm just making a point. In the next step, now I know that the function has two options. 1 minus x in absolute value over x minus 1 has two options because the numerator has two options. Is that okay? So the first option is the numerator to be 1 minus x and the denominator to be x minus 1. Let's write it. But I will factor out negative 1. So this will be negative 1 for x less than 1. I cannot accept 1 because now x minus 1 is in the denominator, so x cannot be 1. The second option is x minus 1 over x minus 1, which is 1 for x greater than 1. Only now I determine the limit as x approaches 1 from the right. 1 from the right is of 1, so the answer is 1. Nothing else. We're not asked to find the limit from either side. It would be DNE, of course, but we're not asked to find that. We're only asked to find the limit from the right. Okay? Any questions on this? Okay. So now I would like to continue with a question from Mason came up with it, and it's a very good question. So here it is on page 117, problem 5. So I'm going to copy it. It says use a graph, and there is a graphing calculator symbol next to it, of course. Use a graph to find delta. Find delta such that we are told that x minus pi over 4 is less than delta. That will imply, it's part of the epsilon delta definition, that the absolute value of the tangent x minus 1 is less than 0.2. Obviously, we know that, what is this? It's the a, it's the little a. What is this? The function, very good. What is this? The limit, very good, awesome. And this is?
Excellent.
Excellent. Great job. Thank you. Okay, so keep this in mind. So here's our first step. Of course, we have to start here and somehow get that as exactly as we did in the past. So then the absolute value of tangent x minus 1 less than 0.2. We looked at a problem similar to this. How does this translate? Don't erase it like that. I'm just making a point. I don't know how to solve this if I don't know how to convert it into something simple that I can solve. How do I convert that? Excellent. Thank you. Tangent x minus 1 less than 0.2. Awesome. This is the correct translation of that inequality with absolute value inequality. Great job. Okay, now, of course, I'm going to clean it up. What will be the next step? How do I clean this up? Of course, I have to add 1. So 0.8 less than tangent x less than 1.2. So keep this in mind. And now, from this point on, we can solve. We have to use a calculator. Ready? Yes, we have this? Okay. So let's go to y equals. Alex, I see your cell phone, so if I see it again, okay, just put it away. Thank you. Please pay attention. Please, I'm begging everyone to pay attention. Okay, so the lower limit is 0.8. I want to graph a function that is 0.8. The middle part is tangent x. Make sure that your your mode is in radian, please. And then the last one, 1.2. Now, I will not just hit graph. We have to think for a moment. That's why I asked you, what does pi over 4 represent? What does it represent in the definition? Little a. So all we care about is a small interval around what? Pi over 4. Okay, so let's go to the viewing window. And let's say I need between pi over 3, I'm sorry, forgive me, I meant pi over 6, 30 degrees, and let's say pi over 2, with a scale of, I'm going to pick pi over 6. And now let's think in terms of the y coordinate, y axis. What do I want? Where am I? Between what and what? Point 8 and 1.2. That's all I care about.
Right.
So I'm going to go between 0.5 and let's say 1.5. That's all I care about. Is that clear, everyone? Okay. 0.5 and 1.5 with a scale of, I don't know, 0.4. I don't care. So now I'm going to graph. So this is our 0.8. Here comes the tangent, and here comes 1.2. Ah.
There it is.
Okay. I needed to think. Okay. So I will determine this point of intersection between tangent and 0.8. I will determine this point of intersection between 1.2 and tangent. Ready? I will use the feature called intersect. Second and calc. I want to find an intersection, 5. It will jump somewhere. It will ask me, is this the first curve? Yes, that's my 0.8. Fine. I can drag it maybe. No, it doesn't work. I just want to get closer to the left. It doesn't matter really. It won't let me drag it, so I have to do this. Okay, so yes, I'll press enter. It jumps to the tangent. Yes, that's my second curve. Just give me the intersect, please. Okay, and it gives me 0.674740. I don't know how many digits we need. So I'm going to write 0.674740. Okay, now I repeat for the other intersection. So now I want, again, second and calc, and I want 5. But this is not going to be the first curve now. This will be my first curve, 1.2. And I'm going to drag. No, I don't want that. I want this to be the second curve, sorry. Okay, 5. No, I don't want that. I want that to be the first curve. No, I don't want that to be the second curve. Yes, I want that to be the second curve. Thank you. Okay, so now it's giving me that other point of intersection. So I'm going to say x is less than 0.876058. I don't need a calculator anymore. And now, okay, remember what we need. We need something like this, which really means negative delta less than x minus pi over 4 less than delta. That's what it really means. So what do you think we have to do to all three sides of this inequality that solves this inequality. The solution of this is this. Well, what do I have to do to all three sides in order to get x minus pi over 4 in the middle? Because it has to be in the middle.
Subtract
Pi over 4 from all three sides. Okay, I'm going to subtract, so, because if I do this again, it's going to take us another 5 minutes. So I will subtract from 0.67 blah, 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 pi over 4. So 0.674740 minus pi divided by 4. And I got this. You don't have to see it. I'm sure you get the same thing. So then x minus pi over 4 is greater than negative 0.110658. And on the other side, 0.876058 minus 876058, yes, minus pi divided by 4. I got 0.090659. Okay. As you noticed, we could have not solved the equation, trig equation tangent x equals 1/2, and we could have not solved tangent x equals 0.8. That's why we needed to use the graphing calculator to solve those two equations. So now I know that I have two options. Not really, but let's write both options. I have the absolute value of x minus pi over 4 to be less than this number, or the absolute value of x minus pi over 4 to be less than this number that will include positive and negative. But we know that we must select the smallest of the two. So therefore, delta is, or anything smaller if you want. So 0.090659. Very good example. We didn't do a problem like this in class, so thank you again for bringing this to class. Any questions? Is this okay? Did you encounter anything else? Do you want me to go back to any problem? Anything?
Do you think we could do number 8 as well?
Is it the same problem?
It's with the E.
Oh, it's the same thing. Instead of tangent, you put E.
Oh, okay.
Yeah, everything the same. So let me take a look at the. You said 8.
Yeah.
Okay, let's give it a shot. I mean, at least let's start it. So this is 8 on page 117. So we have limit as x approaches 0 from E. I think it's 2x, right? Raised to 2x minus 1 divided by x equals 2. Illustrate definition 2 by finding values of delta that correspond. So let's choose which epsilon would you like? Because we could, if we do one, then you can do the other, right? Which of the two epsilon? 0.5. So we have that epsilon equals 0.5. So then x minus 0 less than delta whenever we have the absolute value of e to 2x minus 1 over x minus 2 less than 0.5. Sorry. So we start from this side. I get exactly the same inequality, negative 0.5 less than e to 2x minus 1 over x minus 2 less than 0.5. All we have to do is just add 2 to all three sides and put in the graphing calculator. So when we add 2 to all three sides, we have 1.5 less than e to 2x minus 1 over x less than 2.5, and we have to put in the calculator. From this point on, we can do it by hand. So let me at least show you how to put in the calculator, or is that okay?
This should be good.
So I will put this, and this.
Y1, Y2, Y3.
Yes, y1, y2, y3. And careful, we have to be near
0.
Right. So I will put negative 1 to 1 for the x, because you have to change the viewing window. Otherwise, you will not be able to zoom in and see what's happening. So I'll put between negative 1 and 1. And because we are talking about 2, as you see, so I will go from 1 to 3. So negative 1, 1, 1 to 3. And then find those points of intersection. And of course, you will choose the smallest, as you said. Is that better?
That's all.
Is that sufficient?
Yeah.
Okay, perfect.
I had to simplify it, solve it all by hand, so I was trying to figure out how to divide the X out, bring the
No, you
2X
cannot do
down.
this. You cannot do this by hand.
That's-
That's the reason why there is this symbol here.
Alright,
This symbol tells you that you cannot do this by hand.
okay. Yeah.
However,
I thought that would just be
when
artistic.
we finish chapter 4, you will be able to solve any equation of your dreams, anything. Anything you can think of. Even, just anything. I cannot even give examples. So for example, you will be able to solve this. But we can't do this before chapter 4. And then I'll show you how you determine that solution on your own. You don't need any specific tools. Okay, very good. So we're back to 2.5. Any questions about continuity? Any questions about continuity? I do want to show you a theorem. I'm not going to talk about it. I did talk about it, but we're not using it just yet. But I would like us to, I want to show you where it is, because we will eventually talk about it, and we will basically use it a lot. I know it looks kind of gibberish. Don't even look at all the symbols. Just look at the final outcome. What does this say? I have the limit, I have an operator called f, and I have a function inside. The operator called f goes outside, and the limit operator goes inside. Have we talked about this before? In the limit laws. And we called it not mathematically exact, but we called it swapping of the operators. But this is allowed only under continuity conditions. I do not really care about you memorizing this theorem. That's not the issue. That's not what I'm interested in. I'm interested in you remembering that this is possible and we're going to use it a lot. Swapping of the operators only under continuity conditions. If those are fulfilled, then we can swap the operators. Okay, this is Theorem 8 on page 124. There is no point in discussing it right now other than just that. We're going to use it later. If you remember when we first discussed it, I said under conditions of continuity. So that's what happens. Good. Okay, so, but one theorem that is in this section is extremely important right now and we need it. It's called the intermediate value theorem. Again, this is possible only under continuity conditions, but we are going to discuss it in detail. I normally don't present the general form. I present the specific form that we are going to use. So here is the idea. Let's suppose this is a function. I'm going to ask you a look at the function and tell me whether the function is continuous.
Yeah, yes.
It is continuous. Okay, I'm going to pick an interval. Let's say the interval a comma b, closed interval. And I'm going to say two things. The hypothesis of the theorem. Number one, you already told me the first hypothesis. You said number one, f continuous, at least on AB. If it's not continuous outside of AB, I don't really care. And I noticed, according to the graph, that f of A and f of B are what types of numbers? f of a will be excellent, and f of b will be, we see that, right? So we normally write that f of a is less than 0 in this case, and f of b is greater than 0. Then, this is not working anymore. Oops. Then, by the intermediate value theorem, there exists a C in the open interval a comma b. So this we have not encountered yet in such that f of c must be exactly. Thank you, you saved my markers. Yes, indeed. Indeed. So let's summarize this and then we'll look at an example. What does this really say? It says, let's suppose I cannot solve an equation. But I show that the function crosses the x-axis between a and b because it's continuous. And I realize, and I can prove, that at a is negative and at b is positive, or vice versa, of course. It can be on the left-hand side positive and on the right-hand side negative. As long as it changes sign, I don't care. If from negative to positive or from positive to negative, as long as it changes sign between a and b, and it's continuous, there's no gap, it cannot jump over 0, it's continuous, then there must be a solution between a and b. There must be a 0 of the function between a and b. What is the problem with this theorem? It tells us there is a solution, but it cannot, what? Determine it. It only says there is a solution. Look for it between 1 and 2. I guarantee you. The intermediate value theorem guarantees that number between 1 and 2, let's say. But it cannot tell us what it is. In chapter 4, we'll add to this intermediate value theorem a different theorem. We'll put them together and find any solution we want and solve any equation you can think of. Okay, so let's see how we apply this theorem. The general theorem uses, instead of 0, uses an n. It's the same thing. Okay, so let's take a look at 52 on page 129. The cube root of x equals 1 minus x. The question here is nice. It says, well, look for a solution between 0 and 1. But generally, we're not given the interval. So let's read the problem. It says, use the intermediate value theorem to show that there is a root or a solution of the given equation in a specified interval. But in general, we will not be given the interval. And I'll show you how to determine it. Okay, so first of all, I have to create a function. Creating a function means moving everything to one side and setting it equal to 0, of course. This is our function f of x. Two hypotheses. The first hypothesis is this function continuous?
Yes.
Yes. Yes, the function is defined everywhere, continuous everywhere, but I have to write that. And why? F of x is continuous, at least on 0, 1, but it's continuous more than that, as a sum or difference of continuous functions. That's the key. It's a sum or difference of continuous functions. Therefore, it is continuous. Everywhere. The cube root is defined everywhere, x is defined everywhere, and then -1 is -1. Now I have to find f of 0, and I have to find f of 1. if those values are opposite values, one positive and one negative, I'll say yes, there is a root between 0 and 1. If both of them are positive or both of them are negative, I'll say the theorem is not applicable. So when I plug in 0, I get -1. And when I plug in 1, I get 1. So at this end is less than 0, at this end is greater than 0. By IVT, there exists C into interval 0, 1, such that f of C is 0. What is that C? I have no clue. But it's guaranteed to be between 0 and 1. We prefer intervals that are not wider than 1 unit. If you tell me there is a solution between 0 and 10, I can't accept it. But if you say there is a solution between 9 and 10, I will say accept it. So no, not wider than 1 unit. Pretty easy, right? Right? Okay, perfect. So now let's look at one in which we're not given the interval. So for example, this is my page 5, 56. Same page, 129. We have natural log x equals 3 minus 2x. Same idea, we're asked to use the intermediate value theorem and find what the theorem guarantees, a C between such and such. But we are not given an interval. So we're going to create the function first of all. So plus 2x minus 3 equals 0. So this is our f of x. Now, I know the natural log is continuous on its domain. This is continuous everywhere. -3 is -3. But remember the domain of natural log. What is the domain of natural log?
0 to infinity.
Awesome. Thank you very much. So the domain of the entire function f is 0 to infinity. Very good. So, of course, I will not be looking for solutions to the left-hand side of 0. It will make no sense because the domain is 0 to infinity. Perfect. So then I will plug in this function in the graphing calculator and I will start plugging numbers. Now I have to do this, sorry. So please plug it in. So in y equals, clear everything else. And let's put in natural log. Close the parenthesis, plus 2x and minus 3. And let's go to a second and table. I will not start with 0, of course. Let's see what happens if I put 1 and then 2. I'm done. So at 1 is negative, at 2 is positive. It may have other solutions, I don't care. I wasn't asked to determine all of them. I was asked to find a solution and use the intermediate value theorem. So I know there must be a solution between 1 and 2. Because f of 1 is negative and f of 2 is positive. So therefore, we will write that f of 1 is negative and f of 2 is positive. F continuous, so this should be number 1 and this is number 2. F continuous on at least the interval 1, 2, of course, as a sum or difference of continuous functions. Then we conclude by IVT that there exists a C in the open interval 1, 2 such that f of C must be very good. That's a root or a solution of natural log equals 3 minus 2x or f of x equals 0. Any questions for me, please, on continuity? Any questions? Is there any type of problem that you would like to go back to, or from any of the sections from before, or we move on? Vicky, you wanted something? You had something?
Just looking.
Anything? Anything? Okay, so in that case, at any point in time, you can stop me and I'll stop and if you remember anything. So 2.6, limits at infinity. So let's make first of all the distinction between infinite limits and limits at infinity. Infinite limits versus limits at infinity. So what's the difference here? What do you think is the difference between limits, infinite limits and limits at infinity?
Infinite limits you don't know, limits at infinity are undefined.
No,
I think it's more so like one is like a vertical asymptote and one's like a horizontal asymptote.
that's it. Absolutely. This one is limit when x approaches a from a function, and the answer is infinity or negative infinity. Infinite limits. The result is infinity. And that's it. So x equals a is a vertical asymptote. Limits at infinity. Limit as x approaches infinity or maybe negative infinity from f of x equals, it could be infinity. It could be infinity or negative infinity, or it could be a number, or it could be DNE, whatever. But if it is a number, then y equals that number is a horizontal asymptote. So that's the difference between the two. Okay, the answer here can be anything. But if it is a number, then y equals a, that number is the horizontal asymptote. So the first one, the result is infinity, and the second one, x goes to infinity. So here, y is approaching infinity or negative infinity. Here, x is approaching infinity or negative infinity. So limits at infinity, x approaches infinity or negative infinity. Do we understand the difference? Okay, perfect. Before we look at any limits, and we'll go back to the handout, and I'm going to ask you if you have any questions on that handout. If you finished the problems that I asked you to work on. So let's suppose r is a positive number, rational number. What do you think limit as x approaches infinity from 1 over x to the r power? Let's not use r just now. Let's just use x first. Power 1. And then I'll come back and write this again. But I want to discuss 1 over x. You could say, I have no idea. And then I'll say, yes, you do. Because you know the graph of 1 over x. So you know the answer to this. When x approaches infinity, or in this case, negative infinity, there is no difference. 1 over x approaches
0.
Yes, of course. Therefore, y equals 0 is a horizontal asymptote. And now let's put that r in there, because it can be at any power. So what about limit as x approaches infinity from 1 over x to the r power? R is positive, because if r is negative, then x to the r goes to the numerator. It's a different story. So let's keep r positive. What do you think the answer would be? Of course. If with power 1 is 0, you can imagine with anything else will be also 0, even if it's a number less than 1. But it has to be a rational number. Okay, very good. I like to practice this idea. And you can choose anything you'd like on page 141. 15 through 38. First set of problems that we need to look at. If you have any preference, please choose. How many indeterminate cases have we seen so far out of 7? We only saw 1 out of 7, and that is
When the limit is equal to 0 over 0.
yes. So 0 over 0 is our first indeterminate case that we've seen, and we are going to add on till we exhaust all 7. Okay, have you chosen, or I will? Let's start with an easy one like 18. Is that okay? And then you choose. You're next. So we have limit as x approaches negative infinity from 4x cubed plus 6x squared minus 2, everything divided by 2x cubed minus 4x plus 5. In the previous course, we do not have this operator. We do discuss rational functions. Does anyone remember what would be the horizontal asymptote for such a function?
32.
Yes, 4 over 3. Because same degree over same degree, right? It's that first type of rational function, same degree over same degree. The horizontal asymptote will be the ratio of the leading coefficient over the leading coefficient. Of course, we have to have them in descending order, and they are both polynomials in descending order, leading coefficient over leading coefficient. Agreed? Okay. Let's suppose we don't remember that, because I have to show you how to determine that, or how we determine the horizontal asymptote, or this limit per se. Okay, can anyone tell us what is the degree of the numerator?
3.
The degree is 3. We have to pull out the degree 3. Good. And you can say, but x to the third is not a common factor of the terms in the numerator. And I would say, of course, you're right. Of course, it's not. But I can take it out by force if I want to. X cubed times what is 4x cubed?
4.
Plus x cubed times what is 6x squared? Thank you very much. Minus x cubed times what is negative 2?
X. 2x cubed.
Very good. Awesome. Great job. We repeat the same process for the denominator. What is the degree of the denominator? It's not connected to the numerator, so you do not connect them. If the degree is 4, I take out x to the 4th. If the degree is 3, I take out x to the 3rd. So what do I take out?
3.
Very good. X to the 3rd. What is left in parentheses?
2 minus x over 4. Plus
You meant 4 over x squared. And plus,
5 over x cubed.
that's it. Good. The next step, obviously, I will simplify. And I jumped into my presentation without asking you from the very beginning. Where does the numerator go when you plug in negative infinity? Which of these 3 terms is the most powerful at infinity?
X to the 3rd.
Of course, these are so small they don't count. So when x approaches negative infinity, where does this go? Very good. Same question for the denominator. Which of these 3 is the most powerful at infinity or negative infinity? Doesn't matter.
2.
Good. Where does this go?
Also be negative.
So this is our second case, infinity over infinity. Sign doesn't matter. So So the first indeterminate case is 0 over 0 that we've seen, and now we're looking at the second one, which is infinity over infinity. Good. So now the next steps, we factor out the degree from the top and the bottom, we simplify, and now when x approaches infinity or negative infinity, please tell me where does this go? Where does this go? Where does this go? Don't look. Where does this go? And then we'll write the answer. Where does this go when x approaches infinity? Right, we just discussed that a minute ago, right? So this approaches 0. Where does this go?
0,
Where does this go?
0,
Where does this go?
0.
Good. So what is left from all this?
4 over 2.
Which is
That's it.
2. So which means y equals 2 is a horizontal asymptote at negative infinity. Be very careful. In this particular case, it's a rational function. It's not going to make any difference. But in other situations, for other functions, the horizontal asymptote may be different at one end versus the other end. So it could have a horizontal asymptote that is 2 towards negative infinity and maybe negative 2 towards infinity. It's very possible. So that's why I put that note in there. But it's a rational function. It's not going to make any difference. Both sides will be the same. So we already know 2 indeterminate cases, 0 over 0 and infinity over infinity. And now please feel free to choose any problem you want.
What about 27?
27 it is. 27. Limit as x approaches infinity from the square root of x squared plus ax minus the square root of x squared plus bx. Perfect. It's a very good example because we have a similar example on the handout. Okay. Yes, we have to plug it in. Where does the first polynomial go? Take it slowly, the inside first. Where does the polynomial go when x approaches infinity? Right, because this doesn't matter and this is positive. So where does the square root go then? Of course. In the same way, where does this go? Very good. This is our third indeterminate case. Anything can happen, and no, it's not 0. So we have seen 3 indeterminate cases. 0 over 0, infinity over infinity, and infinity minus infinity. If I have infinity plus infinity, that's not an indeterminate case, that's infinity. If I have negative infinity minus infinity, it's not an indeterminate case, that's negative infinity. But infinity minus infinity, who knows? It's completely unknown. We have to go step by step. Perfect. Look at this function and say, what could we do? Because we can factor. We can subtract them. What is the only option here? Something from our past experience with math. I'm going to copy it because I want to show from the beginning. You don't have to copy it again. So what do you think? When we see radicals, especially square root, what is the first thought that comes to mind?
Conjugate.
Exactly. We have to rationalize the numerator. We normally don't rationalize the numerator. We rationalize the denominator. But this time we have no choice. We have to rationalize the numerator. So what would you rationalize it by? Remember, the numerator and the denominator must be identical because you cannot multiply by anything else but 1. You can change the problem. But multiplying top and bottom by the same quantity, you're not changing the problem. Because you're multiplying this function by 1. Good. So what do we need? The conjugate. Perfect. So what is that?
X squared plus
The square root of x squared plus x plus the square root of x squared plus bx the square root of x squared plus ax plus the square root of x squared plus bx. This is not a trivial situation, so please pay attention. I'm going to copy the easy one, which is the denominator for now. And you're going to tell me what to write at the top, please. And you're going to say, remember we're multiplying a minus b by a plus b. And we discussed this formula on the first day of classes, and we know what that means.
The x squared plus a times x
So x squared plus ax, awesome.
minus
Excellent. Let's put parentheses so we don't forget to distribute. X squared plus bx. Great job. It's a squared minus b squared. So a minus b times a plus b is a squared minus b squared. Okay, we continue. And then we're going to vote if Mason is allowed to pick problems again. I'm kidding, of course. So then we have x squared plus ax minus x squared. So the x squared will go away. So I only have ax minus bx. I hope you agree. Yes or no? Okay. So then the denominator is x squared plus bx plus the square root of x plus bx. This is a, of course. Okay, perfect. The next step, we are going to factor out. What am I going to factor out in the numerator? Yes, of course. And I have a minus b. And now it has to wait. Now, do not look at the square root, but just look at the binomial or polynomial under the square root. What is its degree?
2.
So I would factor out x squared. In the same way, I would factor out x squared for the second one. We have to identify what is left in parentheses. X squared times what is x squared? 1, excellent. And then plus a over x, great job. Thank you, Tara. Okay, the same thing for the second one, right? 1 plus b over x. We agree? The next step is crucial. This is a product. I'm allowed to take the square root from a times b and replace it by this. So I will take the square root from x squared. But what is the answer? Careful. So the square root of x squared, if x can be any real number, is the absolute value of x. Now if you say, no, you don't need this, because x approaches infinity, I will agree with that. But I wanted to give you the general formula. The square root of x squared is not x, but the absolute value of x. In this case, you'll say x approaches infinity, so the absolute value symbol is not important. It's redundant. We don't need it. But remember, this is what it means. X for x greater or equal to 0, or negative x for x less than 0. And see how everything gets connected to everything else we've studied so far. So yes, when I take the square root from x squared, I will not write negative x. I will write positive x only because of this. But if I change this to negative, the answer would be negative x, not x. Is that clear? Okay, so we continue. Okay, from here. So then this is limit as x approaches infinity from x, a minus b over x the square root of 1 plus a over x plus x the square root of 1 plus b over x. Please remember, do not drop the limit operator till the very end, till the last step. Okay, now I see two terms here. I see x as a factor at the top. What do you think I'm going to do as almost the final step?
Cancel the x's.
I can't, not in the sum. I would have to factor out from these two terms in the denominator, what? The only common factor, which is, very good, awesome. I have to write this intermediate step. So x, a minus b, x, 1 plus a over x, 1 plus b over x. Only now I can simplify. And now we're ready to drop the limit operator because we are ready to write the final answer. And it will be at infinity only and for sure in this case. Only. This answer will be only when x approaches infinity. Okay, so when x approaches infinity, where does this go?
0.
Where does this go? Where does the denominator go? 1 plus 1.
Yeah.
Where does the numerator go? A minus b, of course. So therefore, y equals a minus b over 2 is what? Very good. Only at infinity. So it's not horizontal asymptote squared, you know what I mean? I didn't have room. Okay? Yes, this is not a very friendly type of problem, but we needed to see one. This was our third indeterminate case. One more time, 0 over 0, infinity over infinity, and infinity minus infinity. Is this okay? Okay, perfect. Would you like to choose anything else? If not, I would like to look at a function or of an example of a function in which we're given a lot of information, come up with a graph. Are we choosing anything else? Or maybe we should choose something with E. What else? We should choose 38, which is tangent inverse of natural log. And we definitely need to choose something with E.
37.
Say it again.